Although we've done it before, landing on Mars is hard, and this mission is no different. The process to get from the top of the atmosphere of Mars to the surface we call entry, descent, and landing, or EDL. It takes thousands of steps to go from the top of the atmosphere to the surface, and each one of them has to work perfectly to be a successful mission. The process starts well above the top of the atmosphere of Mars. The cruise stage faces the sun. It also has its radio antenna, which faces Earth. But now we don't need the cruise stage. Its job is done. The next step, just 7 minutes before arriving to the top of the Mars atmosphere, is to separate the cruise stage. Before you hit the top of the atmosphere, though, the space capsule has to orient itself so that the heat shield is precisely facing the atmosphere. Now the fun begins. The vehicle is moving at nearly 13,000 miles an hour, but it's hitting the top of the atmosphere at a very shallow angle, 12 degrees. Any steeper, the vehicle will hit the thicker part of the atmosphere and it will melt and burn up. Any shallower, the vehicle will bounce off the atmosphere of Mars. At the very top of the atmosphere, it's about 70 miles above the surface of Mars, and the air is starting to get thicker and thicker and thicker. As it does that, the temperature on the heat shield gets well over 1,000 degrees centigrade, enough to melt steel. Over the next 2 minutes, the vehicle decelerates at a backbreaking 12 Earth Gs, from 13,000 miles an hour to about 1,000 miles an hour. At about 10 miles above the surface of Mars, a supersonic parachute is launched out of the back of the vehicle. 15 seconds after the parachute inflates, it's time to get rid of the heat shield. 6 pyrotechnic devices fire simultaneously, allowing the heat shield to fall and tumble away from the vehicle, exposing the lander to the surface of Mars. 10 seconds after the heat shield is dropped, 3 pyrotechnically deployed legs are released and locked for landing. About a minute later, the landing radar is turned on, sending pulses toward the surface of Mars as the vehicle starts to try to measure how high it is above the surface and how fast it's going. At about a mile above the surface of Mars, the lander falls away from the back shell and lights its engines. And very quickly, the vehicle must rotate out of the way so that the parachute and the back shell doesn't come down to hit it. The last thing that has to happen is that on the moment of contact, the engines have to shut down immediately. If they don't, the vehicle will tip over. So if all the steps of entry, descent, and landing happen perfectly and we are safely on the surface of Mars, we'll be ready to do some exciting new science.
Hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. In fewer than 24 hours from right now, we will be expecting signals from Mars as NASA's InSight mission touches down on the red planet. It's our first Mars landing since 2012, and the excitement is running high. My name is Stephanie L. Smith. I'm with the social media team here at JPL, and with 1 day left to go, we are going to take a little time out. We are going to get up close and personal with some of the scientists and engineers behind this mission. We're going to ask them some questions. We're joined today by our NASA social group. We've got 30 digital creators here in the house at Von Karman Auditorium, selected from over 700 applications from around the world. They're here to ask questions and then share their experiences with friends and followers online. We'll be taking questions here in the house. We will also be taking questions online from social media. Just tag those questions, Ask NASA. All right, so to start us off with some perspective, please welcome all the way from NASA headquarters in Washington, D.C., Dr. Thomas Zurbuchen. He's the Associate Administrator for the Science Mission Directorate, and he's going to tell us how InSight fits into NASA's larger plans of planetary exploration and why it's more than just a Mars mission. Dr. Z?
Hey, thanks. The major reason I wanted to quickly talk to you is just to thank you, first of all. And I want to thank you just because I believe that one of the most important parts of science missions is actually to talk about them. I believe that science, just like in my life, is something that can be life-changing. It's not just because it makes us safer on Earth, because we learn more about our environment, but it can also create careers. Many of the people you're going to talk to have careers that relate to science. My career started with that mission over there, with the Voyager mission. And I remember when I was 8 years old, I got that book at Christmas, and without any engineers or scientists around me, focused on Voyager, and I read it. And of course, for me, that was like a dream, somebody else's dream. But I can tell you right now, and next chart, this is mine, right? So not only is Voyager still there, Voyager 1 and 2, by the way, Voyager just about to make history again. Not going to tease that away. It's all about InSight today. But the point is, we have over 100 missions that are looking at the Earth and looking at many other parts of the world, big and close and far. And for us, what's really important to me is that we tell those stories, not just the stories about science and exploration, but the deeply human stories about doing things that are impossible first. The deeply human stories that have to do with taking something that sounds crazy and turning it into reality. That's what we do each and every day at NASA. That's why we're there, is to break through the boundaries of ignorance, to really go beyond what we can do each and every day. And we do so by building teams. It's not because of individuals. It's by building teams that work and trust each other, teams with different people, diverse viewpoints that come together and do this. And so I just wanted to thank you for carrying that message to your audiences, because the audiences that you listen to you on your social media accounts, hopefully, will be the people that will be there 10 years from now, 5 years from now, 20 years from now, making the next dreams a reality. So I really don't want to add more to it, and I really want to turn it over to Q&A.
I think we've got time for one question in this block, and like I said, we are taking Ask NASA questions online. Let's go to Jason.
Sure. Thomas, so Twitter user NASA Watch has a question for you here, saying that NASA has 2 CubeSat-based spacecraft as a tech demo during InSight. Are you looking at so-called swarm mission concepts, where you only send groups, i.e. many low-cost CubeSats to a world, so that they can do a brief but broad-based simultaneous reconnaissance?
All right, that's a really good question, and the answer is yes. We're learning how to do these small satellites in ways that are beyond their comfort zone. The Marcos, you're going to talk to some of the people who know a lot about the Marcos. They're well beyond the comfort zone of small sat developers. We're extending the range of these spacecraft, their utility beyond that. But one of the things that we're really interested in is in the context of Earth observations, for example. If we fly many spacecraft over in the Earth environment, we can have, if you want, an eye on a given spot at any one time in a way that we could otherwise not afford. So constellations of such small missions, perhaps missions that are even a little bit bigger than these CubeSats, that we can launch together with novel launch vehicles or vehicles that we already have now, are enabling new ways of looking at the Earth, perhaps at the Moon and other planetary bodies. So yes is the answer. We want to do that.
All right, so Dr. Z is very active on social media and is available to answer some more questions after the briefing is over. You can find him at Dr.Dr._Thomas Z. With that, let's give it up.
Hey, thanks.
Okay, so also check out his Science in Seconds series on Twitter. You will learn a lot in a very short amount of time. And speaking of science, that is where all missions start. Science tells us the kinds of instruments and kind of spacecraft that we need to send to answer the big questions. So I want to bring out our starting lineup, our scientists. All right, Flo, so please give a warm welcome to those who are going to tell us more about InSight, how it will get to the heart of Mars with its seismometer, its heat flow probe, and its radio science instruments. Let's bring them on out. Seuss McCarr, InSight Deputy Principal Investigator here at JPL. Philippe Laudet, the SEIS Project Manager from Canes. Tilman Spohn, the HP Cubed Principal Investigator all the way from Germany, DLR, and batting cleanup, Jim Green, NASA's Chief Scientist from Washington, D.C. All right, so our panelists are going to tell you a little bit about themselves, what those fancy titles mean on a day-to-day basis, and just enough so that you'll know what kind of questions you can ask them, and we will spend most of this time doing Q&A. So Sue, I'll kick it over to you.
Okay. Well, good afternoon. I am super happy to be here talking to you today. As you heard, my title is the Deputy Principal Investigator, and the Principal Investigator is the person who is responsible for the science on the mission, the integrity, trying to get the most possible science we can out of this mission. And so I've been helping Bruce Bannert to do that for the last 8 years, and I've actually been here at JPL for 26 years, and I have had the thrill of trying to answer this question: what makes Earth unique? And I've gone about that by studying different disciplines, and I really like to do science at the intersection of different scientific disciplines. So you see this picture of me in the background. I got the fun of going and doing field work in Hawaii, and so we learned about how flows actually occur in the surface, and trying to see the characteristics that we might see of those flows on Mars as well. And I like to study mathematically models of how hot stuff comes up out of the interior of planets to intersect and form volcanism at the surface. So I like to work with geophysics, geology, and I also like to study other planets because they tell us about our own planet. So I've had the thrill of being able to merge those things together. And I just want to say, denial is a technique that I've used to manage a lot of stress. And today, I'm just kind of feeling overwhelmed with the thrill of this momentous occasion of, the decades of work for some of us, the hundreds of us who have been involved in this project. But, beyond just our project, 50-ish years ago, the Apollo astronauts put a seismometer on the moon. They put heat flow probes on the moon. So all that technology was developed, and our, real appreciation of the value of this kind of science for studying other planets. And, just all the Mars missions that have come before us, all the technology that's been developed, even studying the Earth. We've learned about plate tectonics about 50 years ago. So I just feel like it's just this, incredible culmination of all these people's efforts to bring us to this point today. So I'm just feeling very overwhelmed and thrilled to be here and talk to you about it. So to you, Philippe.
Okay, good afternoon, everybody. Thank you very much to be here. So my name is Philippe Laudet. I am working for the National Space French Agency, so sorry for my horrible French accent. And I apologize in advance if I don't understand well your questions, but it's the reason why. I have been working on that project. I am the project manager of the seismometer. The seismometer size is the small thing that you can see in front on the ground, on Mars ground, in front of the InSight lander. So that seismometer was very, very hard to develop, but we succeeded in that, and we are very enthusiastic for that. My job during these 7 years has mainly to be able to face the challenges we had in two major ways. The first one was technical challenges. We were more than 100 engineers in the whole world, hundreds engineers, and we had to face very difficult things because, as you know, this seismometer is the more sensitive that we can do, but as a paradox, it's also the most robust that we were obliged to do because it needs to survive to a launch, to a cruise phase, and to a landing on Mars, and this is not obvious at all. So my job was mainly to help the engineer to find solutions for the technical issues, for the technical challenges, but also to discuss, to prove that it was the right way and so on, to give them the appropriate money to make their work and so on. And the second way I had to work for help in the project was to coordinate all the actors, because you know that instrument is a result of an international consortium. France is leading that consortium, but we had British people who gave us some subsystems, high-frequency sensors. German people gave us the leveling system to make it at the horizontal. JPL gave us the evacuated container on the tether, for example. On Switzerland, make the integration on of all the electronic boards in the electronic box, which will stay under the lander at the other side of the tether. So this was very complicated because we had a very tight schedule, very short time. All these people are in different governments with it's sometimes funding issues. We didn't give them any money because it was without exchange of funds like that we proceed in space activities. So different culture, different money, different schedules. I was in charge of monitoring the schedule in order them to deliver their part and at a good appropriate time in order CNES to be able to integrate as a puzzle of the part of the seismometer, and after to make all the tests of the seismometer alone but complete, and after to go to Lockheed Martin to test the seismometer integrated on the lander. If you I could take to finish an image. That part of my job was as if I was a band leader, as a musician, and I have a very large band who arrive with various musicians, a lot of musicians, like a symphonic orchestra. Every people are playing a different instrument, are coming from different music. Some are classical music, jazz music, rock and roll music, I don't know, Irish folklore, why not? All beautiful musics. They don't know themselves. They are all the ages. They don't speak the same tongue, the same language. And I gave them the most difficult score never written, which has been never recorded before by nobody. So I told them, okay, we have to play the score together, and the concert is very soon. So they did the job. It was very interesting. It was not only a technical adventure, it was also a human adventure. And I am very proud of them because they succeeded to work. It was sometimes a little bit difficult, but now they are very, very proud. And I can tell you that the show and the concert begins tomorrow.
Okay.
Sorry, Tillman.
What a speech. Hi, I'm glad to be here with you today. I'm Tillman Spohn from the German Space Association's Institute of Planetary Research in Berlin, Germany. And I'm the instrument lead of the heat flow probe, or the PI of the heat flow probe. I made a career as a modeler of the interior structure and dynamics and energetics of the Earth and terrestrial planets. And as such, I noticed how important a quantity of characterizing the interior dynamics and energy balance the heat flow is. I mean, the rate of heat that is escaping from the interior. It sort of measures, the rate of the turnovers in the interior and the dynamics, and it is related to volcanism on the surface and even to the rate of generation of quakes, is basically coming all from the heat of the interior. And therefore, I made up my mind that, wow, we're going to have to measure it. And I was in the situation as then director of the Institute in Berlin to say, let's do that. And we devised that heat flow probe that is flying to Mars, and that will be installed in January. Now you see the HP cubed instrument, on the screen. It is basically consisting of what we call a mole. It's not really a mole, but it's a sun that is hammering itself into the ground, carrying behind a cable, installing temperature sensors. And on the way down, we're measuring the thermal conductivity. And after we've installed the temperature sensors, we have the temperature gradient, and the product of both is the heat flow. And when we have that quantity, we will be able to characterize the present energy balance of the interior of Mars. I've been, working with Seuss Mercar, Bruce Bannard, Philippe Lognanet, and others for a very long time of putting a geophysical station on Mars. We became friends, over the years, and we're so happy, to be together on that mission. And I thank NASA that you made that possible. And with that, I hand over to you. Thank you very much.
Thanks very much, Tillman. I'm Jim Green. I'm the NASA Chief Scientist, but that position only started in May. Prior to that, for 12 years, I was the Planetary Science Division Director. And so I had the opportunity to be part of the decision in selecting InSight for this spectacular opportunity of getting down on the surface and making measurements of fundamental importance for the understanding of how terrestrial planets are put together. I'm a magnetospheric physicist, which means that I never met a magnetic field I didn't like, even when they had magnetic fields and then no longer generate their own field. And that's what Mars is all about. However, there's an auxiliary science package on InSight, and that particular package has a magnetometer on it, and that magnetometer will be important in helping understand and help interpret the seismic waves, but it will also be able to measure currents in the ionosphere. And so it's really our first major experiment on the surface to understand space weather effects at Mars. So humans which go to Mars will rely on data from InSight. If Mars shakes, and it does, how bad is that? What kind of structures will we have to build? Solar storms that hit the atmosphere and the ionosphere of Mars, generating currents, how bad are those currents? And will they affect systems on the surface? InSight will tell us these things. A spectacular mission that feeds forward well into human exploration and is a fundamental next step in exploring Mars. Now, I believe that science isn't done until it is shared, and we as scientists do that at scientific meetings. But what we're doing here is indeed having everyone come along, okay? I, like you, are coming along for the ride. There's no button I'm going to push. There's nothing I'm going to do. There's no decision I have to make. I am just enthralled with the process of how we're going to do this magnificent mission, landing it on the surface of another planet. And it is not easy. Just in the last several years, there's been some attempts for landing on Mars that have failed. Are we lucky? When will our luck run out? And when do we have to apply all the engineering that we know to determine what worked right and what didn't work right? These are the kind of things that we're going to find out in the next 24 hours. This will become a valid science mission when those solar panels are displayed like this and we charge the battery back up. Then the mission really will start. And then it's going to be, 2 Earth years on the surface making all kinds of measurements. Now, with InSight is a chip. I said we want to share with the public what we're doing, and that chip's got 2.4 million names of people that wanted their name on Mars. Hopefully, many in this room did that. If you didn't, you'll have to wait to the next mission. So with that, let's get into the questions.
Absolutely. And just like a spacecraft and its payload fairing, we're trying to pack a lot of awesome into a very small space. So if you've got a question in the house, please raise your hand so we can get a microphone to you. Right there.
Hi, I had a question about the mole. I read an article where it was talking about how it works like a jackhammer, and it just slowly hammers down over, I think, a couple of months. And in one of the initial tests, they pulled all the atmosphere out of the test chamber, and it kept hammering itself up. How did they overcome that?
Yeah, I mean, we noticed that the capability of it to enter into the surface depends on the atmospheric pressure. So we made a study, a systematic study, reducing the atmospheric pressure in a pressure chamber. And we found that it works best at the Earth's atmospheric pressure, which is higher, but it still works fine on Mars. But when we go to like lunar, we have to make a different design. It wouldn't work so well on the Moon, but on Mars it should be working. And the pressure is just keeping it, as subtle as it is.
Thank you. Hi. Any chance that we can ID life on Mars, maybe with the instruments on board?
Not immediately, we will be killing the beast if we hit it with the mole. No, I'm joking. But we could, say something about habitability, maybe, but not about life immediately.
So the heat probe is going to give us information about how Mars radiates heat. That will enable a full model of Mars, and then there'll be a certain time or place within that surface for which the heat is enough to maintain water as a liquid. And if there's aquifers down there, Mars has had a lot of water in its past. It's in the rocks, it's under the surface, and if it's below the area where it can actually stay in a liquid form, then you got a possibility for life. So indeed, that would be one of the factors that we look at.
Okay, let's go ahead and take one question from social media, and then we'll come back into the house.
Sure thing. So Pixel Princess on Twitter is asking, how do you actually pick the instruments to put on a lander in order to fulfill the mission objectives?
Okay, if that comes to me, I'd say that's easy. We solicited the best spacecraft that our scientific minds can put together, and that comes then together, as a mission. So this was a solicited opportunity for what's called the Discovery Program, and this was, our top pick in that program for that year. It beat out something like 27 other missions. But Sue, how do you put the instruments together?
Right, so as Jim said, these are competed missions, and so the principal investigators and the science team come together to choose those instruments for competed missions. So in this case, it's driven by our science team and the goals of understanding the interior of Mars.
Okay, let's get a mic right down here.
Thank you. I think you meant back here first, so I'll be.
I guess this is kind of a silly question, but who gets to name these landers and rovers? Is it the team directly, or who gets to come up with the cool names?
Well, when this proposal came in, the name of the mission was GEMS. Okay, GEMS. So Sue, what happened next?
Yeah, so unfortunately, that name was taken by another spacecraft that NASA was flying, I believe, around the Earth. So we had to come up with a new name. And in fact, again, that's the domain of the principal investigator and with input from the science team. So we came up with the new name, and Bruce was the one who got to make the final call. But I was on board with this one, too. So that's how we did it.
It's an acronym, guys.
We like InSight.
Whom among you can give us the full backronym? You guys know about backronyms? You start with the word InSight, and then you back out of it to make the acronym. This is interior
exploration using seismology, geodesy, and heat transport.
There you go. All right. I think we've got time for one more question in the house. Let's get a microphone right down here on the aisle. Oh, there we go. We're just trying to keep it even. Both halves of the brain here.
So we heard from Dr. Banter this morning about this being kind of a dream to get a seismometer on Mars for decades now. What changed? Why now? Why has this all of a sudden become a priority for us?
That's a really good question. From my perspective, it all came together, okay? You have the best instrumenters in the world building the best instruments, the type of instruments that we have, and they're put together as a team, okay? So it's all about getting the right set of instruments to answer a certain set of questions. In other words, those instruments will make measurements. The measurements then are adequate to answer the questions, and that we call science closure. This mission had that. It's now time to select it.
All right, well, speaking of science closure, that's all the time we have for this panel, so please a round of applause for our scientists. All right. We will take more questions online afterwards, promise, promise. Okay, so once InSight lands, she is set to be the chillest robot on Mars. We'll get those solar arrays open, soak up some rays, and feel for the good vibrations. Right? She's pretty deep. All puns intended. I'll be here all week, guys. So to give us a look at the robot's eye view of Mars and show you how you can try your hand at deploying instruments, I want to bring out someone behind a new interactive experience entitled Experience InSight. Please welcome Jason Craig from our visualizations team. Jason?
Hello, good afternoon. Just going to grab a keyboard here. Okay, so I have a number of digital playthings for you to experiment with on your phone as well. Good, it's up here. This is eyes.nasa.gov. This is a site I maintain, and we, first of all, if you don't already have the real-time eyes on the solar system on your laptop or desktop, you should do that right away. But I'm here to show you Experience InSight, and you can go on your phone right now and follow along if you desire. eyes.nasa.gov/insight, or click on the little banner there. First, let's just take a quick look at where we are as far as events live. So this is eyes on the solar system, and there is the holy triumvirate, Marco, A, B, and InSight. So you can see it's not quite close enough to be visually compelling, but I can fast forward. So as we go in, so this is what's fun about the little video game. You can go have a look. See it come into the system, which is rather busy. As you can see, we have a lot going on. And there they go. That's tomorrow. Spoiler alert. Okay, so do check that out if you don't have it. But let's get on to InSight. So this is a real-time well, not real-time. This is a simulation of landed operations for the mission. And anything with a web browser can do this, including those of you who are Linux fans. So that's good. So you go full screen, and the first thing we want to see is you can move around at will. You can go look at what you like. This is actually based on the high-rise terrain from Mars Reconnaissance Orbiter inside the landing ellipse, so we're trying to make it as accurate as possible. It's a real 3D ray trace model. And we can deploy, so let's go ahead and get right down to it. So let's get those solar panels out. Now, on the ground, this will take about 16 minutes, but we don't have that kind of time. So let's just get to it. So it's kind of cool. You're free to wander about and, take a close look. And then we can go ahead. So you can keep hitting the next button to go to the next step, in this case, which will be just this little camera deploying. Over here, so in the bottom right corner, you can see this is the context camera, and we also have this is the context camera, and we also have the arm camera. So let me skip ahead again. Let's go ahead and get that arm going. And note in the bottom right, you get the point of view of the camera itself. So again, we're speeding ahead. This is going to take months. This is going to take months for the actual mission, but you can get a little sneak. There goes the grapple. That's kind of cool, right? This thing just comes off like that. Let's go ahead. On to the seismometer. Gently, oh so gently. I'm going to skip ahead. Let's go ahead and get the windshield. And you can learn about these things. There's text, so you can read more about it and whatnot. But this is kind of cool just to see how it actually physically does these things and puts it on the ground. All right, I'm going to skip ahead. Time is precious. So finally, we are going to break out the heat flow instrument. Do some digging. So this is really fascinating. I don't know if you guys, if you're into geophysics or not, but this is incredibly fascinating. It's you know, once you start learning about it, it's amazing what we can figure out about the structure and evolution of another planet, and even tell us more about Earth itself, which I'm sure you've probably heard already, but the more you get into it, the more rewarding it is. So there it is. And finally, a quick look at what it's going to do. But not that fast. So that's it. You can also go over each and every instrument. So once you have it out, you can just kind of glide over all these and pick one you want to learn about. Like, for example, this is an extraordinarily important instrument on the mission, the RISE antenna, which will do more than any other instrument to figure out, do we have a rocky core or a molten core? What do we have down there? So it's like if you have an egg, a hard-boiled egg and a raw egg, and you spin them, you can tell which one's which. And that's pretty much kind of the same thing with the core. And so we'll detect the wobble of Mars with this and hopefully get some clues as to what's going on inside. And you can look at the antennas and whatnot. And finally, just for fun, you can play with the arm. So once you have the arm there, you can see how it moves. There you go. Yep. Fun, fun, fun. Okay, so that is the software. And please don't forget to go to the website, eyes.nasa.gov, and there's a variety of things there. We also have augmented reality. You can put InSight right on the ground in front of you with Spacecraft 3D and Spacecraft AR. Okay, and I'll be giving demos tomorrow. So with that, I'd like to turn it back over to Stephanie.
All right.
Thank you.
Jason Craig. If you have questions for Jason, you can find him on Twitter at NASA_eyes. So all your questions about that awesome experience and all of the eyes suite of products that he showed. Okay. So before those moments of zen on the surface, there are a few more harrowing ones we have to get through. First, the 7 minutes of terror. Yes, those final mission milestones from the top of the atmosphere all the way down to the surface. Everything has to go just right. So to tell us more about that and about how this spacecraft was made, all of its instrumentations, how they came together, and how we're going to use that robotic arm to get our instruments to the surface, please welcome our engineers. Give it up for Farah Alibay, InSight Payload Systems Engineer, NASA JPL. Aileen Zimmer, InSight EDL Systems Manager, also of JPL. Ashite Trebiolanu, InSight Instrument Deployment Systems Ops Lead of JPL. And bringing in here from Lockheed Martin Space, Tim Preiser, Quality Director. So I am going to throw a challenge out here to you guys to see if we can get through an entire engineering segment without 3-letter acronyms. So we love our TLAs, we love our alphabet soup. It's like speaking another language, but I believe in you. Let's do this. Farah, let's start us off.
So what I heard is we're allowed 4-letter acronyms, just not 3-letter ones, right? So my name is Farah. I'm a payload systems engineer, so that means absolutely nothing to you. But what that means is that my job is to make sure that the instruments and the spacecraft play nice with each other. InSight is kind of an interesting spacecraft in the sense that it's got pieces from just about everywhere, right? The seismometer is from France, the probe is from Germany, the spacecraft is actually built at Lockheed Martin over in Denver. So my job essentially is when we got all of these pieces was to make sure that the instruments and the spacecraft could talk to each other, that they spoke essentially the same language, that they would power on when we told them to power on, that it behaved the way that it should. Basically to make sure that once we land on Mars that the instruments are actually going to work. The other cool thing that I got to do leading up to launch was actually to test all of these instruments. We do all sorts of crazy things with the spacecraft. We fold it up, put it on a shake table, and shake it as hard as we can. It seems like a horrible idea, but the reason why we do that is because by the time we land tomorrow, we want to make sure that that environment it's going to see that it can survive that. We also put it in Mars, well not vacuum, but Mars pressure and temperature and test all of that. So that was leading up to launch, and then my second job is starting, and behind you, you're seeing sort of what the test environment looks like. This is our indoors Mars testbed here at JPL. So yeah, my second job starts actually on Tuesday once we land on the surface. I'm a TAL, and what that stands for is Tactical Uplink Shift Lead, which is terrifying because my job is essentially to manage what we call a tactical shift. We essentially at JPL work when the spacecraft is asleep at night. Obviously, it has solar arrays, so we don't do anything at night. And then when it wakes up in the morning, we have sent it a piece of code, essentially. It's a piece of code that we build together as a team, send it, and then it does that during the day. And at night, before it goes to sleep, it sends us all its data down. It's like, hey, guys, like this is what I did. We look at it and create another piece of code that we send up. So my job is essentially to manage that shift and to make sure that everyone's working together, that all of these different pieces of code essentially are behaving well, and that they're going to do, the spacecraft will do what it's supposed to do. So my first shift is actually going to be Tuesday, and that's when we first turn on the instruments. So I'm super excited about that. But in the meantime, we still have to land. And one of the really neat things about InSight is that there's a ton of young people working on this mission. So for me, it's been super fun. We're all really good friends, and so it's actually really fun to come into work. And one of these young people is Aline. I've actually known Aline since I was an intern. I first interned here back in 2012 when Curiosity was landing. And we were all next door office mates for a very long time. So I'll hand off to her to talk about EDL.
Thank you, Farah. So my name is Aline Zimmer. I am a systems engineer for the entry, descent, and landing team. And the job of the entry, descent, and landing team is essentially to, ultimately the responsibility, as we heard at the beginning of the programming, to take the InSight lander and its precious science instruments from more than 12,000 miles per hour at the top of the atmosphere down to a slow, soft, gentle landing and essentially a full stop on the Martian surface. And all that happens in only 7 minutes. And those are the 7 minutes of terror that you've heard about so much. And I'd like to give you a little insight into, no pun intended, into why I think that is so terrifying. And there's so many layers of terrifying. One is that it's this really carefully crafted and orchestrated series of events that all have to happen perfectly at the right time and at the right conditions for this to go well, for tomorrow to be successful. And that's one thing. But it's not that it has to go perfectly, it also has to be completely autonomous, because while it takes the spacecraft 7 minutes to get from the top of the atmosphere to the surface, the signal that the spacecraft sends back to Earth takes 8 minutes. So when we hear tomorrow in the control room where I'm going to be, when we hear that the spacecraft has entered the atmosphere, the spacecraft's actually already on the surface, and all we can do is sit back and watch and find out together with you guys what happened. And there's absolutely nothing we can do about it at that point. And then the third thing that makes it really terrifying is that historically, as a species, we've not been very good at this, right? From any space agency around the world, of all the attempts of landing on Mars, less than half have been successful. So even though we think, we've done everything to be prepared for tomorrow, and we're confident that we have, there's always that what if, right? That little bit that you may not know about, the you're having a bad day, or that's just terrifying. And so with all this terrifying stuff, I'd be amiss not to mention that this is also really exciting, right? As maybe for you, for me, and I know also for Farah, this is my first time attempting to land on Mars. I'm really excited about that because these opportunities are so rare, right? In this entire decade, NASA has only attempted it twice. So these opportunities just don't come around very often, and I'm really excited and really grateful and honored to be part of this tomorrow. And I'm really excited to be in the MSA, sorry, I messed up.
You can fix it.
I will,
You can fix it. You have the power.
I know. So what we call the mission support area. The control room, essentially. I'll be in the control room tomorrow. I'll be watching the data come down. I'll be listening for these beacons and the tones to hear that the spacecraft is okay. And that's probably the most exciting thing at this point. And then the last thing is, as far as I said, it's really exciting to work in this team. It's an amazing team. It's a bunch of young people, but it's also a bunch of veterans, people that have landed on Mars multiple times. I don't know how many of those are even exist in the world, but a lot of them, right. I was actually going to be my segue. So there's a lot of these people that have so much experience that we get to learn from. And I really appreciate that, and it's been a really exciting time. And with that, I want to hand it over to one of these veterans. Ashite, tell us about Your time.
Hey, thank you. So right now, I just feel like a dinosaur, right? And I don't know what he feels. So this is my 5th landing on Mars. And my name is Ashite Trebiolenu, and I'm in charge of the instrument deployment system. And basically what the instrument deployment system consists of is the robotic arm, the camera on the arm, the grapple, and then the camera underneath the lander. And our responsibility is to pick up the tens of millions of payloads and put them on the surface. The key thing is that you don't drop them, right? Easy to say. And we don't want to end up like Viking, where the seismometer was left on the deck. So my PI, my deputy PI, reminds me of that every day. So before we got here, I was the manager of the robotic arm, developing the robotic arm system, testing it, going through all our environmental testing, the grapple, and I'm sure most people know about the grapple. So if you think about the instrument deployment system, you can think of it as the hands, the fingers, and the eyes of the scientists, right? And the grapple basically is a 5-finger crawl that opens and closes, and it's almost like an arcade one, the one that you see at the arcade when your kids want to pick up those bears and you're never able to actually get them. So this grapple works a little bit differently. So it's always closed. You need to power it on to open it. So the chances of you dropping the instrument is 0, right? So even if you lose power, it's always closed. You actively open it. And it also uses a wax actuator. Basically, we melt wax to open it up, right? And then once it's open, we turn the heater off, and then it closes, right? So we only have an open button. We don't have a close button. Then we have a camera. Our camera actually is loaned from, it's a spare from MSL, Mars Science Lab, Curiosity rover. And then our fisheye camera underneath the lander is from MER. And then the arm that we're going to use in a few days when we land on Mars is also from Mars 01. So if you think about the instrument deployment system on InSight, it's like a kind of used car. So we've got all these used elements, and then we brought them together, and they're from different era. The arm is from what we call the faster, better, cheaper era, where we would try to develop things a little bit faster, cutting corners. So we now have to make it compliant in our new regime that is more rigorous. So we had to go through several iterations and design and testing to be able to get it to be flight worthy. And right now we're transitioning. I'm the lead for the team that would actually be doing the instrument deployment. We have a good group of guys, so 2 ladies and 3 guys, and we're going to have a lot of fun on Mars. I've worked on all the Mars robotic arms from MER, Spirit Opportunity, and I work on Phoenix digging eyes on Mars. We used to call ourselves the grave diggers on Mars. And we're going to do a very unique robotic arm operation on Mars. The first time we're going to pick an instrument off a deck, and we're going to place it on the ground, and we're going to leave it there for the rest of its life. That has never been done before. We usually have the instruments on the arm, we put it down, and we pick it back up. So this is going to be pretty exciting. And we feel very privileged to be working on a mission that will make the footnote of history. So by that, I'll hand over to my friend here, Tim.
Thank you, Ashite. I'm very fortunate to have worked on 9 Mars missions with the folks here at JPL. It's a very powerful relationship in my mind. And the 2 of you have talked about the team that you're building. It's turning into a family. I can tell you my memories of Odyssey was my first, and then MRO. But the memories that I have of those missions are the people, the faces. I can hear the voices and the discussions, and I remember the very conference room and whiteboard that may have been chalkboard back then. But that's the memories that I have of the early missions. I've worked on 4 of the aeroshells, 3 of the orbiters, and 2, including this one, of the landers. And JPL has done just a fantastic job of pulling together, and you've seen them already in this presentation, the best scientists in the world, right? The best engineers in the world, and they're better today than they were when I was there. I mean, they come with the skill set and a toolbox that I could not have imagined. Look at the visualization we just got to enjoy, right? And then Rob Manning, right? Early on, he taught us how that was on a whiteboard, but it wasn't nearly as exciting and informative as the way he was able to walk through that. What I wanted to do, I brought some building blocks of some of the engineering solutions that we have come up with at Lockheed Martin to solve some of those problems. And it's just, 4 pieces of the 1,000 miracles that have to happen at the right time in the right place, in the right order to survive that environment. And I talked to Ashitay just before we came up here. As soon as we cleared the tower back in May, all the EDL guys said, uh-oh, guess what we have to do now? Well, as soon as we touch down tomorrow, Ashitay and the scientists are going to say, uh-oh, I guess we have to deploy and get this stuff on the surface successfully. Every event is critical until it's behind you, and then suddenly the next one is critical, right? However simple or complex that is. And to think about the hundreds or thousands of critical events that have to happen during that 7 minutes. And these folks have been going through that in their minds, on whiteboards, in discussions for the last 6 to 7 years. They've watched it play out in simulations. They've actually been the articles under test in the ORTs, right? So they've lived this. And tomorrow, when it plays out on those telemetry screens, they've seen it already. They saw it in the ORTs. They've seen it when they reviewed data. It is going to be so surreal because they've seen it, right? This is exactly, you don't have to imagine it. You've seen it. You've seen it in the data, right? You've seen it in the tests. You've seen it in your arguments. You've seen it in your nightmares. It's going to play out just like that. So what I've got here is just a simple, this is for the 2,000 degrees, right? Not only does it have to survive heat that can melt steel, which, by the way, we've crafted this concoction of cork powder and some adhesive, and that's what that absorbs that heat. But we also have to survive the 12 Gs of deceleration, right? And the cork isn't very good at structural stability and strength, but we have this honeycomb material that we do use for that structure. And we will actually test the structural loads of the heat shield without the thermal protection system on it for that very reason. So we need to make sure the 12 Gs of a 850-pound spacecraft can be survived structurally, and then thermally, we have this magic, I want to call it cake batter, that we hand pack into this honeycomb material, right?
Speaking of the structural integrity of the show, I think this is going to have to be the last thing that we show. We're going to take one social media question and maybe one more quick question in the house, and then we're going to have to move on because we're almost at the top of the hour.
Perfect. Come up and talk to me. This is cool stuff.
And we'll get hands-on with that tomorrow. So everybody at home, watch hashtag NASA Social, hashtag Mars Landing for more on that. Jason?
Sure. So we have a comment here, actually, from a Twitter user, Steinmonster, who's asking, instead of calling it 7 minutes of terror, can we call it 7 minutes of engineering confidence instead? How are you guys feeling about that?
It would still be terrifying.
So I've actually thought about that. And I was in your seat, and I was terrified. But there is, after we have been able to demonstrate this, starting with MERA and B, then Phoenix, right, then MSL, there are some aspirational changes into expectational changes that have happened to some of the guys that have survived it. So there is a difference, right?
It's scary to us when you're
That's
doing
right.
it for the first time.
The terror does change to something a little bit more confident.
Okay, we got time for one quick question in the house. Let's get a microphone right down here.
Mr. Prizer, this one's for you. I'm going to be filming the answer, so you don't have to look directly at me, but you've worked on 9 missions, correct?
Correct.
So astronauts talk about their perspective changing when they're in space. So I'm just curious how your perspective in your everyday life has changed working on technology that has gone millions of miles away from Earth.
And it's fun because the discussions just like this one also happen in the cul-de-sac at home. When we go into work and we work with our simulations on our assumptions and our fears, and we ask the what ifs and we go off and answer them, that's what we do, right? That is who we are while we come to work at either JPL or at Lockheed Martin or at DLR, right? But when we get to go home and someone asks a simple question, and then you get to answer it, in a conversational way. And then you start to realize, you start to see expressions on people's face that you're doing what? You guys are crazy, right? And it's like, yeah, I guess we are, but it's really, really fun. And it has changed from, a job and a problem to solve to an amazing story that we get to share, and especially when you get to talk to the folks that are single digit in age, right? Their eyes light up, and you can just see what they're going to accomplish in about 15 to 20 years with what we've been able to say, hey, you have a problem to solve, let's solve it with whatever you have on hand, right? Or innovate something new. And yeah, they all start nodding, and they can come up with solutions that we just don't even imagine. Like I said, they come with talents and skills and tools in their toolbox that we just didn't have, still don't. But yeah, it's an amazing conversation. I could talk, and she's going to make me stop, but I could talk for hours with people about what we get to do here. Absolutely. And like I said, we all had Mars aspirations at one point. Some people, and I'm happy that they do. There's a lot of excitement for Mars and the moon right now. But when those aspirations get to change into expectations because, we've done it and we've started to learn from how to do it and to do it better the next time, that's pretty special.
All right. Thank you so much. Let's give it up for our engineering panel. Okay. And in our few remaining minutes, I just want to take time to talk about the spacecraft flying in tandem with InSight on the way to Mars. 2 briefcase-sized satellites called Marco, Marco A, Marco B. To tell us more about them and why they have the nicknames Wally and Eva, please welcome Andy Klesch, Marco Chief Engineer from JPL, and Ann Marinin, the Marco B Mission Manager.
Thank you very much. So as she said, I am the chief engineer on the Marco spacecraft, and this is a full-size model of one of our 2 spacecraft that are headed by Mars right now. As chief engineer, you can think of my role as chief firefighter. On any given day, I could do anything from washing the floors up to actually going into the technical challenges that we have in order to make these spacecraft be successful and support InSight at Mars. And really, we had a lot of work to do to make these things successful because it was a technology demonstration. It was a challenge to us to see what could we do with small spacecraft to support such a large and compelling science mission such as InSight. When we started these spacecraft, we were given just 15 months to go from PowerPoint slides to actually being flight ready on here. And today, I'm proud to say that after traveling 300 million kilometers, our 2 spacecraft are going to be flying by Mars tomorrow. To tell you more about what's actually going on with the Marcos themselves and how they were built, I'll pass you to Anna.
Hi, my name is Ann Marinin. For tomorrow, I will be the Marco B Mission Manager. I've had a couple of different roles on the spacecraft in the only 1 year that I've actually been working on it. And in that year, we've put one together, tested both of them, have launched both of them, and now operated them up until this point. So there's a lot that happened in a very short amount of time, and it was all very exciting. So tomorrow, I will be on console looking at data from the spacecraft and interpreting that data to see how healthy the spacecraft is in its support of InSight entry, descent, and landing. On the spacecraft itself, as Stephanie alluded to before, they're known as Wally and Eva. The reason for that is about half of the internal volume of the spacecraft has fire extinguisher fluid inside, and that is our propellant. So the 2 Marco spacecraft have done their own trajectory correction maneuvers, kind of very similar to what InSight had to do. So we fly by Mars at a very precise time and location. And just like Wally in the movie, we use a fire extinguisher to fly around Mars, or fly around space to get to Mars. So that's why the nickname, and they kind of stuck. So Marco B is the one affectionately referred to as Wally.
There you have it, everybody. A trajectory correction maneuver to get us where we need it to be, where we need to be at the end of this show. A round of applause for Ann and Andy. And a reminder to all of you, please join us online on NASA TV. We're streaming everywhere. Go to nasa.gov/live. Landing coverage starts at 11 a.m. Pacific, 2 p.m. Eastern, 1900 UTC or GMT. Follow us online. We're using #MarsLanding. Follow @NASA InSight for the blow-by-blow, @NASA JPL for news. We will see you online. Go NASA, go JPL, go Marco, go InSight.